Hey class, Adam Ward here. This is our third and final video talking about drag and boundary layers. And in this one we're going to zoom in to see what actually happens right where that fluid is interacting with and affected by the surface. So this is a zoom in to look at what happens sort of at that micro scale, not where we're getting flow separation, but really right at the fluid solid interface. So we're going to talk about both laminar and turbulent boundary layers here. And so the idea of a boundary layer is that this is what happens as we transition from a zero velocity along a surface, so a green plate, for example, here. We've got our no-slip boundary condition right at the plate, and we've got some fluid flow that's approximately the same velocity as it would have been without the plate there. And what happens in between, shaded in blue in this diagram, is what we call the boundary layer. So this is sort of that zone of transition between the no-slip boundary right at the surface and what the fluid flow is doing absent that object being in it. We'll use the notation of delta to describe how thick that boundary layer is. And just by looking at this diagram, you've probably already got the sense that a Reynolds number would be involved. We know in pipe flow, Reynolds number was really critical to us in describing the difference between laminar and turbulent flow regimes. Similarly, that shows up in boundary layers. And so the boundary Reynolds number is what helps us understand or predict where will be the laminar boundary layer and where would be the turbulent boundary layer. You'll remember from our previous chats that keeping that boundary layer turbulent, that was the golf ball strategy, right? We want a turbulent boundary layer because it remains thinner, it adheres to the object, it minimizes form drag. So one strategy about controlling golf balls or controlling the flight of baseballs and soccer balls has to do with controlling rotations and controlling the turbulent boundary layer or lack thereof. For boundary layers, we define a boundary Reynolds number. It's exactly the same as our Reynolds number was before, except that we've got, instead of a diameter of a pipe, we'll actually measure the distance x that we've moved along the surface. And sort of that key threshold to differentiate laminar versus turbulent boundary layers is a boundary Reynolds number of 500,000 or 500,000. So what we're going to do this lecture is zoom in on the boundary layer, see what's happening there, and describe some of the drag forces that would be associated with a laminar or a turbulent boundary layer. What do I mean when I say a turbulent boundary layer? This is a visualization of turbulence, and so what has happened here is a bunch of fine particles have been suspended in the water, and then a laser is used to illuminate those particles at the exact moment that we take a picture. And so you can actually see in this image, you can see some of these sort of rotational sweeps and vortices that are forming. Here's one that's kind of splits as it comes away from the boundary over on the right hand side. Right? So this chaotic motion, losing a lot of energy to rotations, that's what we're thinking of when we talk about a turbulent boundary layer. Okay, so let's deal with laminar boundary layers first. Boundary Reynolds number less than 500,000. And for laminar flow, just like we had with our Hagen-Poiseuille approach, you can solve these kinds of problems analytically. The Prandtl-Blouchis solution tells us something about the thickness of the boundary layer delta, depending on where you are, x, and the Reynolds number. If you take that and you combine it with conservation of momentum in the boundary layer and some of the ideas that we've looked at in our drag lectures already, you can see that derivation in your textbook if you want. You can start to relate the shear forces that you'll experience, so tau. You can relate those shear forces on the left-hand side to the Reynolds number, and you can actually come up with a local drag coefficient. Now, we're not super excited about local coefficients. We've been trying to scale things out to entire objects, a biker, a wing. And so if you integrate this over an entire object, a flat plate, for example, length L in the horizontal and length B in and out of the screen. What I've written here is the exact same approach that we've been using for drag, a coefficient CF multiplied by 1/2 density velocity squared times area. And for laminar boundary layers, what we've written on the left-hand side, integrated over the object, you can come up with a drag coefficient of 1.328 divided by the square root of the Reynolds number. So what do I know? What do I care that you know about laminar boundary layers? I care that you know the differentiating Reynolds number, and that you could look up and apply these equations to estimate drag force on a flat plate with a laminar boundary layer. That's more of a learning exercise to get your head around boundary layers and the ideas of shear stresses and forces than something that you're going to use in practice too often. Now, in contrast, turbulent boundary layers are much, much more common in applications in the environment. And we saw in the golf ball example that if we could make the boundary layer turbulent, it tends to hug the wall. And I didn't really explain that in that lecture. I just sort of asked you to take it on faith. The reason that this happens is that those turbulent eddies, they actually take higher velocity fluid that's farther away from the wall, and as they rotate, they pull that high velocity fluid down toward the object, right? And so what they do is they basically prevent the boundary layer from growing. Those turbulent eddies actually suck the boundary layer down because they pull that free-flowing fluid toward the object. It causes that boundary layer to stay thinner, and because it's thinner and faster, it sticks to the object longer. So we get that narrower form drag. So, the downside of that is you do end up generating higher friction drag from those. And basically from dimensional analysis and empirical observation, we estimate the thickness of the boundary layer as 0.38 divided by the Reynolds number to the 1/5. The local drag coefficient can be similarly estimated, and then you can integrate over an object like a flat plate and describe that with a sort of object scale or an object integrated estimate of the drag coefficient, 0.074 divided by Reynolds number to the 1/5 for a flat plate. As the shape you're interested in changes, so does that equation that you use to estimate the drag coefficient. So again, I don't care so much that you're memorizing these equations, but I care that you can explain conceptually what's different between laminar and turbulent boundary layers. Why does a turbulent boundary layer hug an object or stick to that object longer before it separates? Okay. So the last thing I'd like to do is just one quick example where we're going to look at some of the highest speed trains, the so-called bullet trains in Japan. To give you an example, to give you a sense of what this looks like, here's a bullet train coming through a station. It's not stopping at this station, so you can see just how fast they are. All right, so there's our bullet train. And so the question here is, given some specifications about the car, so typical length of 20.5 meters, a height of 4.1, and a width of 3 meters, for the 6-car train that we watched go by at 275 kilometers per hour, what does it take to operate that? So what's the power that you need to overcome drag forces? Or how much power, how many watts or megawatts does it take just to be able to overcome the drag that you're experiencing on that train car? So to solve this problem, we're going to consider a train car oversimplified as a box. And what I'm going to do is sort of turn that train from the box shape that it really is into a flat plate. And so I'm going to consider that there are two sides and one top. So the bottom of that train is more of a confined space. You've got the train and the maglev tracks below it. So we're going to look at aerodynamic drag, or the drag forces on the top and the two sides of that train. So we're going to envision this behaves like a flat plate that is 6 cars long, so 6 times 20.5 in length, and 11.2 meters in width. And again, that's two sides at 4.1 meters each and one top. And I looked up just typical properties for air at standard temperature and pressure, or STP. And what we can do then is calculate our Reynolds number. And so you see I'm grabbing density of air, velocity of that train, so 275 kilometers per hour. Then I'm converting hours into seconds and kilometers into meters, and a total length of 123 meters. That is 6 times 20.5. Put our viscosity on the bottom, and I calculate a Reynolds number of about 6.3 times 10 to the 8th. So this is absolutely turbulent flow by the time we get to the end of that train car. So with my Reynolds number in hand, I can estimate drag force. And to do so, I'm going to need that drag coefficient. So I'll use the empirical equation we were given, 0.074 divided by Reynolds number to the 1/5 power. Plug in my Reynolds number and I get a drag coefficient of about 0.0013. So I can proceed to calculate drag force. Get my drag coefficient out front, multiplied by 1/2 times the density of air. Next is the velocity term, and so I've converted that 275 kilometers per hour into meters per second here. So that was 76.4 meters per second. And don't forget to square that, multiplied by the area of our plate. And again, we're estimating it as 6 cars long by a top and 2 sides wide. So I come up with a drag force of about 6.3 times 10 to the 3rd newtons. Well, now the problem didn't ask us for a drag force, it asked us for a power, right? And so we can calculate power as that drag force multiplied by velocity. So drag force of 6.3 times 10 to the 3rd newtons, multiplied by velocity, 76.4 meters per second. And I get 4.8 times 10 to the 5th watts, or about 0.48 megawatts. Now, I did look up what's the power to actually run the bullet trains. It's reported at about 4.8 megawatts for steady state operation at full speed. And so what that tells us is about 10% of the total energy that it takes. So 0.48 megawatts out of that that overall 4.8 is going into overcoming aerodynamic losses or drag losses on the train. Where does the rest of it go? Well, the rest of it goes to other power. So for example, those bullet trains are magnetic levitation, so they're using magnets to try to minimize friction losses like spinning wheels on a track. But those are electromagnets, so that doesn't operate for free. That takes energy to keep those things running. So about 10% of the energy in the bullet train is actually about drag. The other 90% of it is going other places. All right, folks, thanks for sticking with me through 3 lectures. These turned out to be a touch longer than I anticipated. I'll try and make that up to you in our next set. But I hope that you can go back and look at the learning objectives for today. Explain something about form drag and friction drag. You could calculate drag forces and drag coefficients and talk about some practical examples of these calculations. Thanks for sticking with me, and I'll see you all back in class. Have a good one.